Large-scale data analysis was pioneered by Google with the MapReduce paper. Since then, Google's approach to analytics has evolved rapidly, marked by papers like Dremel and Dataflow. Dremel combined a column-oriented distributed file system with a novel way of processing queries. A single Dremel query is distributed into a tree of servers, starting with the root server, splitting into the intermediate servers, and ending with the leaf servers, which talk directly to the file system. Once the data is pulled from the file system into the leaves, the data propagates back to the root server and is shuffled along the way so that the root server receives a sorted response. When Google started turning its internal services into customer-facing cloud products, the effort to productize Dremel began, and BigQuery was born. Jordan Tigani is an engineering lead who works on BigQuery, and he joins the show to discuss the evolution of the data warehouse. Large-scale distributed queries still can take a long time, but the queries get faster every year. Queries that required a nightly Hadoop job 10 years ago can be viewed in a frequently updated user-facing dashboard today. Power users of BigQuery talk about the speed and the query interface as being two of the most valuable differentiating features. As the job of a large-scale data analyst becomes less technically intensive, tools like BigQuery will continue to rise in popularity. We've done some great shows about Google papers and products like Spanner and Dremel and Dataflow, and you can find these old episodes by downloading the free Software Engineering Daily app for iOS and for Android. In the other podcast players, you can only access the most recent 100 episodes. With these apps, we are building a new way to consume content about software engineering. And these apps are open sourced at github.com/softwareengineeringdaily. If you're looking for an open source project to get involved with, we'd love to get your help. Shout out to today's featured contributor on the Software Engineering Daily open source project, Shreyans Sheth. Shreyans has worked on the Software Engineering Daily search API and has also helped us to understand some open source best practices, which we are still learning. Thanks again, Shreyans, for your work, your contributions, and your commentary. Now let's get on with this episode. Amazon Redshift powers the analytics of your business, and Intermix.io powers the analytics of your Redshift. Your dashboards are loading slowly. Your queries are getting stuck. Your business intelligence tools are choking on data. The problem could be with how you are managing your Redshift cluster. Intermix.io gives you the tools that you need to analyze your Amazon Redshift performance and improve the tool chain of everyone downstream from your data warehouse. The team at Intermix has seen so many Redshift clusters, they are confident that they can solve whatever performance issues you are having. Go to intermix.io/sedaily to get a 30-day free trial of Intermix. Intermix.io gives you performance analytics for Amazon Redshift. Intermix collects all your Redshift logs and makes it easy to figure out what's wrong so that you can take action, all in a nice, intuitive dashboard. The alternative is doing that yourself, running a bunch of scripts to get your diagnostic data and then figuring out how to visualize and manage it. What a nightmare and a waste of time. Intermix is used by Postmates, Typeform, Udemy, and other data teams who need insights into their Redshift cluster. Go to intermix.io/sedaily to try out your free 30-day trial of Intermix and get your Redshift cluster under better analytics. Thanks to Intermix for being a new sponsor of Software Engineering Daily. Jordan Tigani is an engineering lead at Google. Jordan, welcome to Software Engineering Daily.
Yeah, thanks for having me.
We're going to talk about BigQuery today, and to get people acquainted with what BigQuery is, why don't you explain what a data warehouse is and what people are looking to get out of the idea of a data warehouse?
That's a great question. I think a data warehouse has sort of somewhat of an old school pedigree. It comes from people with large data systems that maybe perhaps aren't necessarily large by today's standards, but they tend to have a very specific idea of what type of data they want to store and how they want to store it. There's sort of like the Kimball method of sort of data warehousing, of how you structure your data with fact tables, dimension tables. But it's really for, that enterprises use a data warehouse to analyze reports over their data. It's almost been sort of like, it's sort of very, structured is not the right term, but it's very somewhat narrow how they're used. And I think BigQuery is a data warehouse, but we're also trying to be a little bit more than a data warehouse. It's analyzing any structured data without worrying about how the data is laid out. You don't need a DBA. You don't need a lot of the database optimization that people are used to in their data warehouses, because the way BigQuery is designed, that everything is a table scan, that we can do things that are usually slow very fast.
Mm-hmm. Well, I think data warehouse has a connotation that historically maybe you just use it to get these nightly reports and it aggregates this data in an offline fashion. But with BigQuery or with other newer, more modern data, what we might have called data warehousing systems in the past, now we call them maybe data engineering or something else. We might take data from a production database and put it into the data warehouse, but it might not just be used, this data warehouse might not just be used for nightly reports. It might also be used for actual, functionality, application functionality. How do you think about the usage of a data warehouse for serving user requests? Is it for that also, or is it just for offline calculations?
I think it absolutely can. I think you get to actually one of the important part about a data warehouse is that it is separate from your sort of online database, where you have, your database has the current state of whatever's happening. And it's very important to have, high numbers of transactions, high numbers of updates per second. And you can almost think of the data warehouse as sort of the log of all the things that happen to that database. And you want to be able to analyze that without impacting what's happening on the online side. And I think there's the kind of, you build up the nightly reports for the executives that look at it in the morning, and they can see how the business is doing. But there's also sort of the ad hoc analysts being able to figure out, they want to ask questions about the data. Maybe they're going to do some predictive analytics, or maybe they just want to build some charts. They want to test a hypothesis. And I think there's also can we turn this over to customers? And when the customer hits your website, can it run a query? Mm-hmm. And that's also something that's made possible with your data warehouse in the cloud, especially with something that will scale out nicely like BigQuery, where you don't necessarily have to worry about tightly controlling the load or who gets access to it.
Mm-hmm. And the reason I wanted to do this introduction is to give people a perspective for the past, that this data warehouse was largely an offline thing that was sort of hard to deal with, but it's gradually become lower latency. It's become easier to deal with. And one of the tools that enables that is BigQuery. And now that we have that introduction, I want to start to frame what exactly BigQuery is. I think it's a storage system, but it's also a system for querying that storage. Give your explanation for what BigQuery is.
Okay, so I usually say it's a large-scale SQL query engine and a structured data store. And one of the nice things about BigQuery is the sort of the separation between compute and storage. You can scale your query ability completely separately to how you scale your data storage. And the query engine is this sort of massively parallel, multi-tenant shared pool of servers that basically pick your SQL queries apart, send them out to individual shards, where each one of those shards operates over a small portion of the data, and then there's a number of aggregation stages depending on how complex your query is. So it's this sort of dynamic shared multi-tenant pool of query resources. And then it's also a structured storage system that, scales out to petabytes, many petabytes, and is designed to sort of manage your data so that it allows fast analysis to your data. For example, something that, if you have sort of perfectly sharded data, you can often get much faster query performance, and it doesn't matter what type of analysis system you're using. And that's one of the things that we try to do is people are constantly adding their data over time, maybe in small chunks, maybe in large chunks, maybe, what the weekends are small and the other days are large, or maybe they're streaming at an inconsistent rate. And, we make sure that the data is sort of in the right shape to be fast when the user wants to query it.
The speed of BigQuery is largely enabled by Dremel. Explain what Dremel is.
Okay, so Dremel is a internal tool. Actually, one of our engineers built when he was essentially tired of waiting for MapReduces to finish, and MapReduces were too slow. And while he was waiting, he's like, "Oh, column stores are cool. I'll build a column store because I only need to access a few columns out of this wide data set, and then I'll build a SQL parser, and then of course, since it's Google, we'll make it scale out, and we'll make it scale out to as far out as we want, because that's sort of just the ethos here is sort of scaling out versus scaling up." So as they built this sort of, this is sort of a 20% project, and he got a couple other people working on it, but it turned into like this, the system that was extremely popular at Google, and it has sort of, it's a tree structured analysis. So that I mentioned that your query sort of gets picked apart and passed down to the shards. They're the sort of the lowest level of the tree is where it sort of directly accesses the data, and then aggregations happen at higher levels of the tree. So that was sort of the initial version of Dremel. It's since gotten a bit more dynamic, especially since queries don't always just sort of have a single aggregation phase. But so Dremel is this execution system that, I guess the other key point of it also is just that it's multi-tenant. So we can have a much larger tree and devote a lot more resources to each individual query because we have lots of people using that same tree. And sometimes one user is going to be using it heavily, and sometimes another user is going to be using it heavily, and we can sort of fill in the gaps and end up devoting a lot of computing power per query.
A thank you to our sponsor, Datadog, a cloud monitoring platform bringing full visibility to dynamic infrastructure and applications. Create beautiful dashboards, set powerful machine learning-based alerts, and collaborate with your team to resolve performance issues. You can start a free trial today and get a free t-shirt from Datadog by going to softwareengineeringdaily.com/Datadog. Datadog integrates seamlessly with more than 200 technologies, including Google Cloud Platform, AWS, Docker, PagerDuty, and Slack. With fast installation and setup, plus APIs and open source libraries for custom instrumentation, Datadog makes it easy for teams to monitor every layer of their stack in one place. But don't take our word for it. You can start a free trial today, and Datadog will send you a free t-shirt. Visit softwareengineeringdaily.com/Datadog to get started. Thank you to Datadog. Let's save the execution engine and the query serving part for a little bit later. Talk a little bit about the storage. You're going to store this data in columnar format. Can you explain the advantages of columnar storage?
Sure. Columnar storage, you can think of it as instead of storing in a file, you store one row at a time. That's sort of traditional row-based storage. Columnar storage, you could also think of it as storing a single file has one column, and we often sort of concatenate those into a single file or at a single location in a file. But effectively, it's you have all the data for a single column is contiguous. So the advantage of this are most queries don't access all the columns in the table. you might have 300 columns in the table and you access 4. So if you have a row-based storage system, you really have to read all of the columns for every query, which makes it inefficient because often you end up being I/O bound. So the speed at which you can read data off of whatever media it's on is the limiting factor in your query. So if you only have to read, a few percent of that, that's going to be, you can get an order of magnitude or 2 orders of magnitude performance improvement. The next bit is compression. So if we compress the data, that means we have to read less of it. That means we can essentially effectively go faster. And the compression across a row tends to not get very good packing, very, very high compression ratio, because compression works by eliminating redundancy. And there's not a lot of redundancy across a row where you have a username and a customer ID and an order ID. There's not a lot of shared information there. But if you look just at say the customer, the state in which they live, there's 50 states in the U.S., so there's only 50 fields that could possibly have, but maybe those are spelled out. So those essentially can be compressed very highly. And our storage system. Well, I could get into that a little bit later, but those are the primary benefits. And you can also play interesting games with the storage that sort of get into some more technical details that are opened up by a column store.
Mm-hmm. In order to put this data in columnar format, are we often taking it from a row-based format, like a production database, like my user's database, and then reformatting it in a columnar way in order to store it and serve it in the manner that would be useful to the type of BigQuery queries that we're getting?
Yes, essentially, from the user perspective, they don't have to necessarily worry about how we're storing it. They give us the data in the format that's convenient for them, and we support a bunch of formats, including CSV and JSON and Avro. We're currently sort of alpha testing Parquet as well. So these are all these all except the latter are row-based formats, and so the users are kind of responsible for getting the data, out of their database or wherever they have it stored and into one of those formats. There's also another option, however, which is streaming, and so you can take, and I think actually long term this is going to be probably the most interesting way to write your data. So you can basically send a single rows or single clusters of rows and just send an HTTP post request to BigQuery, and those immediately get added to your table. So if you send this request, these 10 rows, you get an HTTP 200 back, and then you run a query immediately afterwards. That data will be returned in that query. And if you think about large data sets, pretty much all large data sets are created over time, and so really they're created. The data comes in some sort of streaming fashion. And what we think of is, we often take, a day's worth of data and load that at a time. These are sort of like just fixed windows on the stream of data that's coming in. And I think as we sort of have better and better tools, we're going to just start seeing more people just want to operate over streams and stream their data in and not worry about having to collect it and batch it periodically.
So the columnar storage had been used in different ways prior to Dremel being built, but Dremel allowed for some faster and more parallel query response. So let's get into the idea of a Dremel query. Describe what happens in a Dremel query.
So your query comes into BigQuery. We figure out where the table is, where the data is stored. We kind of route it to the right production data center. And it starts talking gets assigned a query master. And the query master is, I guess you can think of it as sort of like a MapReduce master, and it's responsible for figuring out how many workers you need, how many partitions are in the table, how to actually plan the query. So it generates a query plan, can talk to the scheduler to basically say, I need this many shards, and then the query then gets, the scheduler assigns it some shards that it can run on the shards or the workers, and then the query gets dispatched to the shards. And so if you're just doing like a select sum over some field, the way you can implement that is, the way you can do that in parallel is, each you can send that out to 1,000 different workers, and each one of those 1,000 workers reads one file, and each one computes a partial sum, and then you basically send it to some sort of aggregator, and the aggregator computes the sort of total sum over those partial sums. Then you have the final result. Obviously, that's a very simplistic version, but in general, that's sort of a two-stage query. There's the bottom stage, which is the scan and partial aggregation. The second stage is the final aggregation. And in general, in BigQuery and in Dremel, in between those stages, the shuffle, and it's a sort of a fast in-memory shuffle operation. You can think of a shuffle as a sort, but you generally don't need to do a full sort. It's just sort of a hashing, so where the things that look the same go to the same place. And in this case, where we have this really simple query, that wasn't needed. But let's say we were doing a group by. We're doing a group by user ID and a sum, and sort of the group by would mean that all of the values with the same user ID would get shuffled to the same location, and then that one worker could operate over all the values with that ID. And so you can do those in parallel, and that you can operate as if you have all the data for that user in that one shard, and then there might be maybe a final aggregation stage as well.
Right. To recap, this Dremel query executes as a tree. The root server is going to talk to a collection of intermediate servers, and each intermediate server might be talking with more intermediate servers, and these are called mixers. And then at the bottom of the tree, the leaf servers, because they're leaves, because they're at the bottom of the tree, they're querying the distributed storage layer, which is probably Google's file storage layer, the Colossus layer. And then the results are aggregated back up the tree and then reduced into a simple response. Can we go into the roles of those different node types in more detail, the mixers and the leaf servers and the root server?
So what you've described is exactly what's written in the Dremel paper that I think was in 2006.
A little dated.
So we often talk about things in that same way, just because they're easier to understand. But for the last, I guess, 3 or 4 years, it's a different system. So the original system with the mixers and the root mixer and the intermediate mixers and the leaf servers was very fixed, and it worked super well for certain things. It worked super well for just sort of like simple scan, filter, aggregate queries, but it didn't work very well for things like joins, or things where maybe you want to do an aggregate by do a group by one key, and then you want to group in an outer query, you do a group by another key, or you were doing analytics queries. So there's sort of a bunch of things that just sort of required something more complex than this simple tree, and you'd end up having to do multiple traversals of this tree. The current version of the system will dynamically, you can sort of think of it as dynamically building that tree. So the sort of the scheduler, as that I mentioned, the scheduler and the root mixer, they sort of figure out how many levels of the tree that you need, and we'll build that tree on a per query basis. So we still have the low level, the initial nodes at the root that are directly reading the data and doing sort of the first level of querying, and then the next phases are often doing aggregation, but they also might be doing a join, they might be doing a union, or they might be doing analytic functions, which often would otherwise require a separate traversal of the tree. So it's a much more dynamic system, and sort of much more efficient, because you only essentially have to make one pass through the tree. And the other thing that is key is so sometimes you can pass data directly from one to the other. So in the initial Dremel tree, it was essentially an RPC that was happening from the mixer to the nodes, and then they'd return with some partial data, and that would cause problems, because if the amount of data that had to be returned was larger than can be returned in a single RPC, then you'd often get these errors, resources exceeded errors. And so now, instead of directly passing data back, we sort of pass data back through this shuffle layer. And this shuffle layer lets you kind of expand the amount of data passed in between layers in the node to be much larger.
Now that we've talked a little bit more about the distributed query execution engine, what's the ideal way to have this data laid out in the storage system, given how we're going to be executing queries against it?
That's sort of one of the things that we try to do as sort of the magic of BigQuery. Often we have, there's a certain size of data that you want basically each one of these workers to be operating on. If we make that size too small, then we spend all of our time opening files. If we make that size too large, then we don't get much parallelism. Say if you have 100 megabyte table and all that data is in a single file and it's only operated on by a single worker, you don't get any parallelism. So there's sort of this sort of data optimization layer that goes on that tries to figure out, based on the query history, how should we distribute this data? There's also, you can partition your data, you can partition it based on a date field, and that'll also kind of determine how your data ends up being laid out on Colossus.
Dice helps you accelerate your tech career. Whether you're actively looking for a job or you need insights to grow in your current role, Dice has the resources that you need. Dice's mobile app is the fastest and easiest way to get ahead. Search thousands of tech jobs, from software engineering to UI to UX to product management. Discover your worth with Dice's salary predictor based on your unique skill set. Uncover new opportunities with Dice's new career pathing tool, which can give you insights about the best types of roles to transition to and the skills that you'll need to get there. Manage your tech career and download the Dice Careers app on Android or iOS today. You can check out dice.com/SEDaily and support Software Engineering Daily. That way you can find out more about Dice and their products and their services by going to dice.com/SEDaily. Thanks to Dice for being a continued sponsor, and let's get back to this episode. Talk more about that file storage layer, Colossus, and the interaction between the leaf nodes and Colossus. Or I guess you said it's not exactly the same naming convention as the leaf nodes anymore, but what's going on in that query layer, the direct layer between the nodes and the storage layer where they're querying it from? Like, you just describe the interaction between the leaf nodes and the storage layer?
Sure. So Colossus is sort of the successor to Google File System, to GFS, and it solves a lot of some of the scaling problems that GFS had. Colossus divides up the data access into, there's two basically things you want to talk to. One is the curator server, one is the D system. And D ends up living, one of the interesting things about the way the Google data centers are laid out is that we have this distributed storage system and we have these sort of containerized, workers, and the same machines that run the workers also, in general, also host the disks. We don't really try to have locality where you keep the data local to the same machine you're operating on. In fact, we sort of do the opposite. We try to spray it across as many disks as possible. And this gives you a super high overall throughput. So if you're reading from all those hundreds of thousands of disks at once, the effective throughput that you can get is incredibly high, which is how we can some queries we can run almost as fast as some in-memory queries, even though we're reading it off of spinning disks. We have the Colossus Curator. The Colossus Curator sort of tells us, hey, this is where the data lives. We may say we give it a path and has a bunch of files, and it says, okay, this is where those files live. These are the D servers to talk to, and then the nodes will generally talk to the D servers to pull pieces of the capacitor, which is our file format. Pull pieces of the capacitor files files back, data tends to be sort of in reasonably small stripes. And so if you're thinking about the data in a column is stored together. One other advantage of a column store is that, let's say we're reading, it's a 100 megabyte file and we're reading, 3 columns, and each one of those columns is say 1 megabyte. So each one of those columns is going to come from a different D server. So instead of having to do three different seeks and 3 different sort of take the same disk spindle and have it to read all this data, we can actually read all that data in parallel.
How does a query on BigQuery compare to a MapReduce query?
It's interesting that they're very much a dual of each other. Like when we had the tree structure of Dremel, it wasn't as clear what the mapping was, but actually it's quite similar now. I mean, MapReduce tends to be, map, combine, shuffle, and reduce. And so, the mapper is in BigQuery is sort of the shards which are doing essentially the scanning of the data. We combine and shuffle that happens in we actually do have a shuffle involved. And then the reduce would be sort of where the aggregation happens. But like in MapReduce, when most interesting problems you want to solve, most interesting things you want to ask of your data can't really be represented in a single map and reduce phase. And so, we might end up having, map, shuffle, join, reduce, and then join again, and then reduce again. It lets us be a little bit more flexible, but I think sort of modern MapReduce systems also can do the same thing.
Could you maybe give an example of a query that would be a good fit for Dremel and one that would be a good fit for MapReduce?
So I think that anything that would be good for MapReduce would be good for Dremel.
Okay.
I think writing out large amounts of data, that's not even true anymore. It used to be that writing out large amounts of data would be better in a MapReduce than it would be in BigQuery, but we can write out data from the shards, so I don't think there would be an advantage to using one versus the other. MapReduce tends to be more sort of static. You spin up a pool of workers, then you have this sort of static pool that you own completely, and it's used entirely in this computation. But if especially if it's a large computation, you may only need all of those workers for a small portion of the operation, but yet you're stuck with them. So you either have to sort of over allocate the numbers of workers you have so that the one phase that needs all those, that is super wide can execute quickly, or you under allocate, in which case you don't have a lot of idle workers sitting around, but the kind of the part of the query that's most data intensive may execute more slowly. And that's sort of one of the advantages of BigQuery we have, and Dremel is sort of this dynamic tree that we will allocate different numbers of shards for each stage of the query, and we can actually dynamically adjust those. And then the rest of them essentially can get used by other queries.
For people who are new to the concept of a data warehouse or who are new to BigQuery, talk a little bit about the usability and how the patterns for people using this. For example, how often, if I have a production user database and it's getting updated with new user data every day, and as I've got a user interactions database as well, and I want to pull this data into BigQuery on some schedule, and then I want to be able to run analytics queries on it. How am I using BigQuery? How do I set it up to pull that data from my production database into essentially my data warehouse, or whatever you would call it, the BigQuery storage layer?
So that's something that I have a little bit less insight into than perhaps some of the internals, but we see a wide range of how people are doing this. I mean, some people are they're generating events, and those events get streamed directly to BigQuery. Sometimes they have an hourly or a nightly batch process that extracts the data that they need and loads it into BigQuery. I think what we often find is that the period will decreases over time. So people will often start with okay, I'll take my daily dump of my database and load it into BigQuery, or I'll take these large batches, and then over time they realize, oh, it'd be great if I could have, things that were within 4 hours. And so we'll have everything in 4 hours. And then they'll be like, well, 4 hours, why not 4 minutes? And they'll, do smaller batches. And then, 4 minutes, why not 4 seconds? And then they'll start using the streaming system.
Yeah, makes sense. BigQuery is this public productization of what was an internal tool in Dremel. And at this point, Google has done this with several products. It did it with Kubernetes, but Kubernetes was kind of a rebuilding of the Borg project, and TensorFlow, but TensorFlow was a rebuilding of the Disbelief project to become open source. I suppose those open source projects are a little bit different, but in any case, this process of productizing and externalizing internal Google services has become a pattern at this point. What has Google learned, or what have you learned specifically about productizing internal projects?
I think one of the things that we learned that it's hard. When we first started the BigQuery project, we were like, oh yeah, we'll have this done in a quarter. And in fact, we've sort of seen that over and over again. I don't want to call anybody out because, but there have been another number of projects where they've been like, yeah, well, this is a very mature internal product. Like this, works very well. We'll just, put an external API on it, and then, and then that's it. No problem. So I think the thing that we've learned is that it's hard. And there's a number of reasons for that. One is, there's just some impedance mismatch things, just in terms of sort of how auth is done internally and how auth is done, authorization and authentication are done externally. And those are the things that are frustrating, but you can't really get around. And I think we've sort of gotten better at that. It's sort of like, as our systems at Google are converging, we have better ways for dealing with that. But certainly at the time, I used to say, there's some quote that says like the only hard problem is in computer science is naming, and I added and authentication, and just because it sounds like it's relatively straightforward, but ended up being difficult. Other hard things though were at Google, all these sort of internal monitoring and systems that are in place so that when something goes wrong, you can figure out what happened. There's the status pages of the Borg workers, and there's all these like tools that people are used to digging into what happens in when something goes wrong.
Oh no!
And that's really hard to replicate for external users, because you don't have that level of detail, and moreover, you don't want to give them that level of detail because there's a security risk of sort of letting people know, like, map out your data centers. Sort of B, you want to kind of give them sort of some higher level representations of what happens. So partly so they don't have to worry about the details, but also partly so you can change them in the future. So that was a major difficulty, and we're still sort of dealing with that. We see people who are using BigQuery, and when something goes wrong, they don't really know how to solve their problem, or how to
serverless.
Yeah, exactly. The problem with magic is that when the magic doesn't work, you're left with like not knowing what to do or how to make it magic again.
And I can just imagine the engineer who joins the BigQuery team and is thinking, "Oh, I can't wait to work on the new query execution engine," and then it's day one, like, you're working on authentication for the next 3 months.
I think one of the cool things is that there are all kinds of engineers, and some people like really want to work on the guts of the SQL engine, and some people like solving security problems, and some people like
totally
more customer facing side of things. But certainly there are some pieces that are more sexy than others, and some stuff that just sort of has to get done.
Yeah. Okay, well, I guess, final question, when you look back at the evolution of how BigQuery has evolved since the Dremel paper, what are the biggest milestones that you would point out in how if we are talking about the actual, the guts of the file storage and the query execution layer, what are the milestones? What were the big breakthroughs of figuring out new ways to do this more efficiently?
So there was Dremel X, which was sort of a major effort that kind of rewrote the rewrote the guts of how execution happens in Dremel. That was really the thing that changed it from being this sort of static tree that's in the Dremel paper to a more dynamic one. There was Capacitor, which is our new columnar storage format, and that was, I think we had some 10x improvements from that. One sort of milestone just was it was a team one, but we merged the Dremel team and the BigQuery team, and that was done several years ago. But instead of thinking of BigQuery as a layer on top of Dremel, it became more of a collaboration, and especially as the core Dremel folks realized that, hey, this is our primary customer, our primary use case now, and that enabled us to sort of think much more deeply about how to solve enterprise customer problems as opposed to sort of how do I solve the problems for the ads teams. And one interesting thing we learned is just sort of like how different external customers are from internal ones. And there was a lot of sort of disbelief about that in the beginning. It's just like, oh yeah, well, we can handle multi-petabyte queries that there's no problem. These external customers have much smaller data, won't be a problem. And it turns out that doesn't always reduce that way.
Jordan Tigani, thanks for coming on Software Engineering Daily.
Thank you very much. Appreciate it.
Wonderful. Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily.
Wow!